that is a bit annoying. Anyway, I'll write it on the board. It's fine if it doesn't come on in the recording. It's not a big deal. So this is the setting we're looking at. So you have a verifier, okay, and then you have prover 1 and you have prover 2. Okay, so the verifier is classical. Okay, and there's going to be one message sent from the verifier to the prover, similarly one from the verifier to the prover. Okay, and what we want to do is we want to verify BQP computations. So we want it such that if the answer is yes, that the system can convince us that it's yes, and if it's no, it cannot convince us beyond a certain probability, right? So we want completeness and so on, it's the usual things.
And provers, what are the assumptions on provers?
The assumptions on the provers at the moment are, so we're assuming that they're unbounded when they're malicious, and when they're honest, they are essentially BQP. I think that's enough.
And they're not communicating, or they don't?
Yeah, sorry. That's the key assumption, that they don't talk to each other.
And they don't have any shared entanglement previously?
They can have entanglement. In fact, they will need entanglement. Yeah. Okay. So that's the setup. Okay. So we are going to basically use. So I'm just setting up the preliminaries, right? So the preliminaries are fine, right? It's just defining the norm that we are interested in, which is going to just be the maximum singular value. Pauli matrices are identity xz. Sometimes we use identity xz for the operator. Can you turn off these lights? Thank you. So the it doesn't know which are which. Okay, good, got it. Thank you. Is this focused? It's probably me not wearing my glasses, that's why. No, it's good. Okay, good. So we're going to look at, so these identity x and z, you'll see from the context. Sometimes they'll mean Pauli matrices, and sometimes they mean the observables used by the provers. They had some stuff, like they had different fonts in the paper. I didn't realize, so I just wrote it like this, but they are different. Okay, we're going to look at non-local games, self-testing, and Pauli braiding. These are the three things. So non-local game and self-testing we did last time, right? So here's just setting up some notation. So the game would be denoted by G. Omega star would be the highest value of the game, right? And what we want to argue, or what self-testing basically says, is that if you're close to omega star G, then your provers are essentially using the ideal strategy up to some isometries, right? Okay, so the game that we are interested in for this specific work is going to be the magic square game. So the game is as follows. So you have a verifier, okay, and the verifier sends a number R from 1 to 3 randomly, and number C from 1 to 3. So R denotes the row and C the column, and the provers have to answer with two numbers, A1, A2 and B1, B2, which are both plus minus 1. Okay, and you define A3 to be the XOR of the answers. So A1 XOR A2 gives you A3, okay, and B1 XOR B2 gives you B3, right? Yeah, but yeah, that's true actually. I think they may have messed up the notation. Yeah, so they're probably taking a product. They're probably thinking of it as minus 1. Yeah, thank you. That's a good point. I didn't catch it. And then the verifier accepts if AC matches B sub R, right? So you just have to match it. So that's the game. The claim is that classically you cannot do better than 8 by 9. Okay, and quantumly you can win with probability 1. And the strategy involves having two EPR pairs shared. So two EPR pairs, not 1, 2. And on question R, the first prover performs a measurement in the first two columns of row R. Okay, so this is the matrix of operators. So on question R, it's going to measure the first two columns. So suppose if R is 1, so it's going to measure the first two columns. So this and this operator to get the values for A1, A2, right? And if if it's Bob's turn, then you do the opposite. So Bob would be specified a column, and he will measure the first 2 rows in the column to give the answer. Okay. So that's how the construction works, and you can check that the product of the first 2 rows gives you the third row, and the product of first 2 columns gives you the third column. Okay, and then so from this you can see that A3 and B3 would be consistent, just by construction. Okay. So yeah, so we'll not get into the details of this. We can look at it later, but roughly that's the game we are interested in. The interesting part about this game is that it allows you to show that if you win with probability close to 1, then one can prove that the provers are sharing exactly 2 EPR pairs, and the measurements are close to the honest Pauli measurements up to local isometry. Okay, because like it's basically all the Pauli matrices, right? So it has X, and Z. So you can argue this. Okay. So somehow we won't be too worried about Y, because we look at Hamiltonians which are only of the X, Z form, but okay, that's the point. So the lemma is basically just formalizing the statement I made, that suppose you win with probability 1 minus epsilon, and the provers were using some state psi and some observables W, then there's going to exist some isometry V, which goes from the Hilbert space of the prover to C2 tensor C2 and some extra Hilbert space, such that the isometry acting on the state would give you the 2 EPR states, right, that we mentioned. So tensor 2 and some auxiliary state which we don't care about, and also that for W being one of the, so these are observables at the moment, they are not Pauli matrices. So whatever observables the prover was using to answer the different questions, they are essentially up to a local isometry, so which is VA dagger, the same as the Pauli matrix. So sigma sub W basically corresponds to the analogous Pauli matrices for X and Z. Is it making sense? Yeah, sorry. Yeah, when you show it like this, it can go really fast. Just slow me down if it's not clear.
So first statement is about the state share between provers.
Exactly, and the second is about the measurement made by the first prover in this case. But I guess the analogous statement also holds for the second prover, but we don't need it here, so we don't bother too much. Actually, that's not true. Oh no, it's true. Yeah. Sorry. Because every time I see 2, I think there are like the 2 provers, but each prover is making 2 measurements, right? So that's why. Okay, and the distance is the error scales as root epsilon. So, okay, great. So that's the game that we were looking at. Now the Pauli braiding test is the next thing. So a Pauli braiding test is basically something that allows the verifier to certify that 2 provers share T EPR pairs and perform the indicated measurements consisting of Pauli observables. Okay, so you're able to establish there are T EPR pairs and that you're making measurements which are the Pauli observables. Okay, so it's basically sort of a generalization of the magic square, right? So for magic square you had 2 EPRs and you were making Pauli measurements. Now you're able to do it for T EPRs. Okay, and we'll define PBT in just a moment, but
So these things essentially work if you have local structure kind of thing. You can check if the prover has two EPR there, but if I just want to have single prover, then nothing else is solving my thing.
yeah, that's the whole compiling business, right? Because then you have to use computational assumptions somehow. So this was not known before Mahadev's work, how to do any of these things with a single device.
Yeah, then EPR is not in the picture, right?
Yeah, because there's no notion of spatial separation, right? EPR only makes sense when there's some notion of spatial separation. With one prover, it's very difficult to argue that there are 2 systems that are not communicating. Okay, any other questions? Is it okay? Can we go on? Okay, so now there are 2 things. So the first is that I'm just magically hoping that the pen starts to work. It was very nice. I thought in the last lecture it would be cool. Okay, so there are a few things. So the first one is the syntax. Okay, so the prover is going to ask T Pauli observables to be measured, but only X, Z and identity. Okay, we're not considering Y here. y causes some more subtleties. So the prover is going to ask one of these w's to be measured, and each prover is going to be asked this w, right? So it's a t-bit string, if you like, or a t length operator, whatever, right? It's not a bit, right, because there's 3, so it's a trit, whatever. And then each prover answers with a t-bit string. Instead of bit, it's plus minus, right? That's fine. And the notation is the following: that for w in x, z, t, and a in 0, 1, t, w a sub I is wi if ai is 1, and otherwise it's identity. Okay, so a is basically sort of an indicator function, right? So wherever a is 0, you basically substitute it with identity, and if it's 1, then you pick the corresponding element from the sequence w. Okay, so for example, if w is, so if w is like this, right? So if it's a x x z x, for example, and your a is say 0 1 1 1, so then w of a is going to be essentially this identity x z x. So basically, wherever there's a 0, you just replace it with identity. That's all. Just notation. Okay. And yeah, which you can also write as what I've written here, that you take wi and then you exponentiate. That's fine. Okay, so the honest strategy is that the provers share t EPR states and measure sigma sub w, basically the corresponding Pauli measurements. Okay, so that's the honest strategy that would be used, which is also what we did for the magic square. It's essentially the same. And self-testing says that even if the provers use an arbitrary state psi, right, and make some projective measurements, but they pass with 1 minus epsilon, then the state and these observables are going to be close to Pauli measurements and t EPR pairs. Right, so that's essentially the same self-testing statement informally stated. Is that okay? No, somebody is getting lost. So I haven't said much, right? So all I've said is that, so each prover is going to be, so you're going to ask w, right, to each prover. They're going to answer with some a and b, right, which are t-bit strings. And then the claim is that if, suppose they win with probability close to 1, with probability, say, close to 1, then the state that they were using has to be, EPR pairs, so 5 0 0 tensor t, right, and then there's some junk here, right, and then the measurements w that they were making would be up to isometry. So this is like up to isometry and close. Okay, so this little squiggly thing, it's not exact, so it's going to be essentially the corresponding measurement, Pauli measurement. That's all I'm saying. I'm not saying anything very deep. Okay. All right. So now we actually describe the procedure explicitly, right? So the procedure has 3 parts, and each of these steps is done with equal probability, so 1/3. So the first step is a consistency check. So what you do is you check the measurement performed by both provers are essentially equivalent, and the way you do it is that you ask the first prover to perform, say, tau sub w a, and the other one does tau sub w b, and then you check that the answers match. Okay, because you're interrogating them separately, they don't know which operator was asked of the other one. So if they're making different measurements, it won't really work. Then linearity testing is the following: you check that, you ask so you want to make sure that this relation is true. But I'm actually a bit confused now. Let me check, because if I ask the first prover these questions, wait, let me check. So my concern is, okay, so the thing that we want to make sure is that, if I ask TWA to be measured and then TWA prime to be measured, then it's essentially the same as TWA plus A prime. So that's the notion of linearity. But what I'm a little concerned about now is that the same prover, you're only asking one question, right? So it's a bit less clear. Oh, okay. I think, wait, did I not write the whole thing properly? Okay, sorry, yeah, I skipped a few steps. Okay, this is just informally stating the three things. We'll formally state it in just a moment. Okay, so linearity test is you want to test this property. Okay, so we'll see how the actual protocol proceeds, because obviously you can't ask the same prover to do this. They can just lie, right? So you have to ask two different provers, but we'll see how to do it. But this is what you're testing. And finally, the anti-commutation property that you're testing is that the prover's measurements essentially follow the same commutation and anti-commutation rules that are consistent with honest measurements. So that is like whatever, so suppose tau were the actual things they're doing, then they should essentially follow the commutation. So this is the commutation that's followed by Pauli's, right? So the number of x's and z's that don't commute, it's just counting that number. So wi not equal to wi prime, and ai's basically have to be 1, right? Because if it's identity, everything will commute. So you restrict to the ones where there's non-trivial things happening, and then you count the number of times that you have either xz or zx, right? And the number of times you have xz or zx, when you flip the order, you'll pick those many signs. So it's just counting -1 to the number of signs, right? So that's fine. Say it again, sorry, louder. Yeah. So this is what we want to test. Exactly. So how we test it, we'll see in just a moment. But yeah, these are the properties that we want to test. Okay. So linearity and consistency are relatively simple. We'll describe it in just a moment. For the anti-commutation, we'll use the magic square game. Okay. And then this will allow us to conclude that they have the correct number of EPR pairs and they're making Pauli measurements on it. So these other two conditions are needed because there are many systems, right? So you want to argue that you can measure tensor products of many Paulis. So you can do it individually, but you also want to argue that you're actually measuring tensor products of different Paulis and they're actually consistent. So it's for that reason that you've added. We'll not do the proof for this, but at least I'll give you the construction of how it is, what the game looks like. So the consistency test is as follows. So the verifier picks an n-bit string w, picks an n-bit a, sends w a. Maybe there should also be identity here, no? Did I miss it? Yeah, there should also be identity here, I think. Otherwise, there's no need to do WA, is there? No. Actually, no, it's fine. There is need to do WA. Otherwise, if there was identity already, you didn't have to do A. Sorry, my bad. Okay, so you sample W, and then you sample A, and then you send WA to Alice and also to Bob. So you send the same questions, and then you accept if the answers match. Okay, so that's just consistency, making sure that they're both making the corresponding measurements. Linearity test is the following. So in the linearity test, what you're doing is you pick W, again xz, and then you pick two different AA primes. And what you do now is you send, you pick W prime randomly between WA and WA prime. Okay, so you pick one of them. So to the first prover, you send both WA and WA prime. To the second prover, you send only W prime. Okay, and then the provers answer, and the answers are say BB prime and C. So then what you're going to do is you're going to test that B actually matches C when W prime was WA, or B matches C prime when W prime was WA prime. Okay. Huh? Yeah, sorry. So B prime should be equal to C prime. Thank you. Yeah, I can't correct it. Oh, yeah, exactly.
There was no C prime, right?
Yeah, B prime should be C, right? Not, yeah. Thank you, yeah. Oh, my pen's not, but I can write actually. Oh, I can still type, can't I? Maybe I can, let's see. Oh, okay, so B prime equals C. Oh, it's because it's dark mode, that's why. Okay, good. All right, and then finally the anti-commutation test. So the anti-commutation test is you play magic square games, many games in parallel. Yeah.
How is this linearity?
Yeah, so I think I was actually also thinking about this. I was also not fully sure because I didn't look at the proof. It is likely doing linearity testing because the first prover is likely measuring both WA and WA prime, and I think the order is not making the
What did you say? WA plus A prime into G.
it must be equivalent. I think that's, or maybe that is what is, no, actually I'm not sure.
They're not sending A plus A prime anymore.
Yeah, that's true, that is true. I agree. Let's see. Linearity test. Yeah, that's what it says in the paper, so I'm not sure. No, it's a valid point. I actually don't know. I'll have to look at the proof. I have not looked at the proof. But the bottom line is that that's the property that you want to test. It's also not clear WA prime.
W prime is just one of them.
Yes, it's not clear what they are measuring, whether they're measuring both WA and WA prime to compute BB prime. Probably, right? So you first measure one and then you get the other, and then yeah. Okay. Let's move on. Unless we do the proof, I don't think it's going to help to speculate too much here. All right. So the theorem by Natarajan and Vidic is the following. So they showed that this thing actually corresponds to it's the formal statement of cell testing, right? So if you do that test and your WA correspond to observables, then and you win this game that I just described, the linearity test with probability 1 minus epsilon, then there exists some isometry which would basically allow you to deduce the same thing, that you apply the isometry on the state, and then the state is close to t many copies of the EPR state. And if you were to take the operator W, right, and conjugate it with the isometry, then it's essentially the same as the operator being applied by the observable. Okay. So that's the statement, and of course you can apply V. Yeah, you can also apply V on the other side if you want to get the EPR. But okay, this is enough for our purposes. And finally, the statement. Yeah, this is just a trivial statement, right? It's trivial in the sense that because it's by construction, that if you use EPR pairs and the observables you use are Pauli matrices, then you'll pass the test with probability 1. Okay. So that is the theorem. All right. Okay, so that completes the prerequisite sort of thing. No, it doesn't actually. It's still on section 2. Sorry. So the last prerequisite we'll need is the local Hamiltonian problem. So the local Hamiltonian problem is the following. So you start with the quantum analog of maxat. So the problem is as follows. So you take the Hamiltonian H, and you write it as sums of these little Hamiltonians H sub I, and these little Hamiltonians H sub I act on at most k qubits. Okay, so that's why it's local. Otherwise, it would be just a general Hamiltonian. And you are promised that one of these two is the case. So either there exists a state with energy at most alpha. Okay. So you have there is some state which has a low enough energy, right? So it has some state which has energy less than alpha, or you're promised that all states have energy greater than beta. Right? So it's sort of like, so this is the energy spectrum, if you like. So it's saying that either there exists, so case 1 is there is some psi, right, which has energy lower than this, or it is the case that, so case 2 is that all states have energy higher. Okay, so you have that. So this is the promise that there'll be this gap basically. H sub I is a Hamiltonian that acts on at most k qubits. Right. Okay. All right. And then the local Hamiltonian problem is QMA complete for k equals 5 and the gap being 1 by Pauli. Okay, so QMA complete means what? you probably know this, right? That it's basically, if you don't know, then it's the quantum analog of NP, right? That we discussed a bit in the previous lectures. QMA complete just means that you can, if you had a solver for the local Hamiltonian problem, you could solve essentially all QMA problems. So if you had a way of, given such a problem with such a promise, if you had a way of distinguishing which case you're in, then you can solve all problems in QMA.
So what will be a certificate for all case? For there exists case, I can give a string.
That's QMA, right? That's how is an NP problem defined? You have a certificate only for the yes instance, right? You don't have a certificate for the no instance.
Yeah.
Just the same. Sorry.
We have the restriction that beta minus alpha is greater than equal to 1 by point or something.
Sorry, I didn't hear the starting of your question.
For the k is equals to 5 case, we have the restriction that beta minus alpha should be like greater than equal to 1 by poly. For all other, in the general case, what is the restriction or like relation between beta and alpha? Is like alpha always smaller than beta?
Yeah, so these are parameters. So for different parameters, you will have different kinds of hardness. So it could be that the problem becomes, so for example, if k is 1, which means the Hamiltonian is non-interacting, right, then the problem might become easy because, so it depends on, like, of course, and if k is like completely general, it might get even harder than QMA, for example.
So, can I say that
Can it get harder than
alpha
QMA?
is lesser than beta?
Yeah, to make the problem non-trivial, I guess you have to choose some parameters. So normally we are thinking that beta is greater than alpha. Yeah, that's true. Right. Okay. So here we consider a specific variant of the local Hamiltonian problem, right? So the way I described it, it just said that the locality was just appearing in these terms, right? And the only constraint was that this hi terms act on at most k qubits. Okay, but the variant that we are going to look at is called the xz Hamiltonian, and here each term acts on is just a tensor product of sigma x and sigma z. So in addition to being local Hamiltonian, the terms in the Hamiltonian also have this specific form. Okay, and also sigma identity. Okay, so the xz Hamiltonian is defined by these parameters. So there's k, which is the locality parameter, alpha beta, which we already discussed, and alpha is strictly less than beta, like you were asking, right? Then the xz Hamiltonian is the following promise problem. So suppose n is the number of qubits in the quantum system. You'll be given as input m values, so gamma 1 to gamma m, which are going to be the amplitudes for each of the Hamiltonian, the weights of the Hamiltonian terms. And then you'll be given the Hamiltonian terms themselves. And these Hamiltonian terms are going to be of this form, that there'll be sigma x, sigma z, sigma I, like I said. And the number of terms that are non-identity would be at most k, right? So it's just formalizing what I said earlier, that there are at most k non-trivial sigma x, sigma z.
And when you give Hamiltonian, so these are like bit strings. How do you give these?
You have some canonical description because you're just specifying xz, right? So you just give a classical description. It's not a problem, right? Okay, and then the Hamiltonian is just this. So it's 1 by m sum over j, gamma j, hj. Okay, and one of the following holds. Like I said earlier, there exists some state which has energy energy at most alpha, and then for all, so that's one case, the yes case. In the no case, it would be the case that for all psi, energy would be at least beta. So like I described over there.
Some of HI.
Yeah, h is just defined. Oh, you mean the normalization? Is that what you're concerned about? 1 by m?
No, the gamma G here times H.
Yeah, because we restricted the form of h, right? So we said h is just a Pauli matrix. So we have to explicitly add the amplitude. Earlier, hi was just some Hermitian matrix acting on k many qubits. Yeah. So we could absorb the normalization in hi. Yeah.
So this assumes that you can perform measurements. So you give me classical description of the Hamiltonian, and you assume that with that classical description, I can perform measurement of quantum state to like verify these expectation values.
Yeah, but this is like a very simple circuit, right? It's a very simple. Basically, you pick with probability gamma, which hj you want to compute. It's expectation, right? So you'll just have Or maybe do you think there are cross terms? No, it's just h, right? So psi is the same, yeah. So you pick with some probability. So if h is, say, gamma I hi, right, sum over I want to compute psi h psi. So this I can write as I gamma I psi hi psi, right? That's just the expectations. I've not done anything. And the circuit for doing this would be like, with probability. So with probability gamma I, choose hi. Hi is a local circuit, right? It's just applying some Pauli matrices on at most k qubits, so that I can measure given psi. So that would give me on average it would give me this expectation, right?
Yeah, I'm thinking that this given circuit,
Mhm.
what does it mean that okay, so you are applying circuit on this thing?
Yeah. Basically, I need to compute this expectation, and I can do it by running a very simple circuit because of the structure of the Hamiltonian. Of course, you cannot do it in general, but because we have like a very local.
Even for HI, so suppose you have simple Hamiltonian.
Yeah, you can do it in size Pauli of k, where k is the number of qubits h is acting on. Not Pauli actually. It would be, it could even be exponential, but as long as k is not scaling, like if k is a constant, you can do it with a constant size circuit.
Actually, you choose the measurement in the basis of HI.
Right. Yeah, or whatever procedure is given. Yeah, exactly. Okay. Any other questions? All right. So this is fine, and then what we're going to do is we're going to look at. Okay, so why we are considering this problem will become clear in a bit. But the nice thing about this problem, this specific problem, is that it is still QMA complete. So even though we restricted the form of HIs, right, to just being sigma z, it still continues to be QMA complete. All right. And this is what the lemma formally states, right? So it says that as long as the gap is 1 by Pauli, there is some constant k for which xz k local Hamiltonian is QMA complete. Right? Okay. And it's still open whether one can show that k local Hamiltonian is QMA complete for when the gap is constant, while maintaining k to also be constant. This is not known. So one can achieve the gap by having k depend on some parameters, but that's not what we want. Okay, that was just a side remark. So here is a lemma that I guess we'll be using at some point later. So the lemma says the following. So it says let H be an n-qubit Hamiltonian, right, and the minimum eigenvalue is strictly greater than 0, and the highest eigenvalue is at most 1. Okay, and suppose alpha and beta are at most 1 by Pauli, are at least 1 by Pauli. I suppose it should be the difference. Maybe I wrote it wrong. Lemma 4, lemma 5. Yeah, I suppose the difference should be 1 by Pauli, I guess. I'm not sure here, but okay. Let's see what the statement is. So the statement says that you consider H prime to be the following Hamiltonian. No, I think it has to be alpha minus beta, right? Otherwise the inverse could explode, so we don't want that. So beta minus alpha is, so you consider the following Hamiltonian beta minus alpha inverse qubits. Okay, so you have, okay, so this is the form of the Hamiltonian. So you're starting with a bunch of identities and subtracting some n many of them, adding the original Hamiltonian and subtracting some identity again and taking tensor product. Okay, whatever. This is some Hamiltonian that you constructed using H. The crucial thing to note here is that you're only adding identities, right? So you're not. So if it was sigma xz in the beginning, H prime will also be sigma xz, right? So if H had only x and z terms, then H prime will also only have x and z terms, right? That's kind of clear just from the construction. Yeah? No? Okay, and then if so if it is the case that the smallest eigenvalue is at most alpha for the initial Hamiltonian, then for the final Hamiltonian the smallest eigenvalue will be at most half. So you're amplifying the gap to constant essentially. Okay, and if the value is at least beta, then you can make it such that the new Hamiltonian has the lowest eigenvalue at least 1. Okay, so instead of taking alpha beta, you can do like 1 and half. So that's the key thing. All right. And finally, it will be useful to define what we call non-local games for Hamiltonians. We're doing good time. I'm happy. We'll probably be able to finish it today. Okay, so non-local games for Hamiltonians are defined as follows. So given a local Hamiltonian H acting on n qubits, you produce a non-local game GH with one verifier and r provers, which has the following properties. Okay, and for the properties we'll need these parameters, so alpha, beta, C and S. So alpha is strictly less than beta and C is strictly greater than S. So C is the completeness parameter, S is the soundness parameter, alpha, beta are the energy levels that we've been discussing, right? So what we want from the game is that when it is the case that the smallest eigenvalue of H is at most alpha, okay, then the game can be won with probability C. So the maximum value of the game, so omega star, is at least C. Okay, so when there is a low enough energy state, there should exist a high probability of winning. So in the game it should be, you should be in this case. So it's completeness and soundness, right? And if you're in that case that the energy is greater than beta, so there's no low energy state, then you want to be, the game should not let you win with high probability. Huh? Oh, it's just the notion of completeness and soundness, right? So the convention is that if it's a yes instance, you want the game to accept, and if it's a no instance, you want the game to not accept. And the way we define a yes instance is there a ground state with low enough energy? So if there is, then you want the answer to be yes, right? Nothing very deep. Okay, so this is the definition. We haven't given a construction. If we could do this in general, right, then we were in good shape. So we'll see how to do it. All right. So now, yeah. So that was all the prerequisites. Okay. So now we can.
In the previous explorator,
Uh-huh.
we came up with the new extension. I mean, is there any like inclusion or idea of like why we is the one and how did we come up with that?
Oh no, I didn't. Like I said, like all of these things, I've not looked at the proofs, so I have no intuition for. And the paper also doesn't say much about how these are doing, what they're doing. Yeah.
It's fine because it kind of nicely whatever we want. If we want less than alpha, it like pumps it up till less than half.
Right. Yeah, it's some kind of amplification, but I'm not sure if it's immediate.
It's fine.
I can tell you what reference it's in. You can look it up. Number 40 is. Oh, it's in the same Natarajan Vidic paper, the one that had the linearity test. It's in the same paper that I haven't covered yet. Okay. All right. So now we do section 3. So section 3 is 1 round 2 prover games for local Hamiltonians. So now our goal is to prove the following theorem. So the theorem is that there exists a universal constant delta such that the following statements hold. So suppose the Hamiltonian is this. I'm not sure whether this 1 by m factor is actually there in the statement or not. Okay, it was a little bit less clear, maybe a typo. But suppose the Hamiltonian is of the form that we said, so it's xzk local. Okay, on n qubits, and it has parameters alpha, beta, where beta is strictly greater than alpha. So if you have this, okay, then there exists a 1 round 2 prover non-local game. So exactly of this form. So 1 round. So you send 1 message to each, you get 1 answer. 2 prover. Such that if the lowest eigenvalue of the Hamiltonian is low, right, then the verifier accepts with probability at least half plus delta. Okay, and if all energies are greater than beta, then the verifier accepts with probability at most half plus half minus delta. Okay, so you have a constant gap. delta, which is independent of, so it's just a constant, doesn't depend on the problem instance. Okay. Or the scaling parameter actually. And additionally, the length of the message being used is n into beta minus alpha inverse. Okay. So if you have, even if you have inverse Pauli gap, you'll still require only polymany bits of communication. Okay. So the objective in the remaining lecture is to prove this theorem, assuming all the stuff that we've stated earlier. Okay. Any questions? Okay. Uttam bhai, you look very concerned. Everything okay?
So you will use non-local games.
Yes. Yeah. So the proof strategy here is that, yeah. So the one thing which we are not, why I wanted to cover this is because later there is a way of compiling non-local games, right? So what you can do is you can run the, so this is what, what's his name? Venkata was also saying, right? That you can compile these games. So there's a procedure where, so suppose this was Q1, this was A1, this was Q2, A2. So there is a procedure where you ask Q1 under FHE, you get answer A1 under FHE, ask Q2 in the clear, get A2 in the clear. And then often one can show that you can inherit the properties of the non-local game in the compiled setting as well. But that's a lot more work, which is what I wanted to do, but I think we just ran out of classes, so we won't be able to do it. But at least we'll see one verification. That's one of the building blocks for doing it in the single setup. There are also other ways of doing it, but I thought maybe this would be nicer because you can do even stronger things than just verification. Okay, so now, right, so let's start then. So you start with the non-local Hamiltonian, non-local Hamiltonian, I'm saying exact Hamiltonian, right? And we do it in two steps. And the first step, what we do is we construct a non-local game called a Hamiltonian test, GH, based on H. Okay, so it takes H as an input, produces a new game. And we are able to argue that the maximum acceptance probability, omega star, right, which was the value of the game, right, that we said. So we're going to show lower and upper bounds corresponding to the smallest eigenvalue of the Hamiltonian. So we're going to make that correlation. And then once you have GH, we'll construct another non-local game G tilde H, which amplifies the gap. So if the initial game had, it might have like some correlation to lambda 0, but lambda 0, remember, is related to alpha and beta, which are not necessarily constant apart, right? They may have some inverse Pauli dependence. So this new G tilde game amplifies the gap to half plus delta and half minus delta. Okay, so the second step is relatively straightforward. Like reading it is relatively straightforward. Coming up with it may not be. But the first step is what will take a lot of work. Sorry, this was a problem with the scan. It's the same page again. So let's start by describing this Hamiltonian test, which is based on the Pauli braiding test that I mentioned and an energy test that we'll add now. Okay, so here's an informal description first, and then we'll do the formal description. So the provers share T EPR pairs, okay, and the first prover holds a copy of the ground state of H. Okay, so there's two provers, one of them has H. Okay, so you give it the witness psi ground state. Okay. The other prover doesn't have this. Actually, even if it does, I don't think it makes much of a difference, but that's the setup. And in the energy test, what the verifier will do is the verifier will pick an L from 1 to M. It will pick a W as before, XZ, T many of them, and then it will pick an E, also a T-bit string. And now here's the new part. It will choose T1 to Tn. So I've written them as tau, but they're actually T, okay, because later he uses tau for something else, and I didn't know at the time. So T1 to Tn as basically indices. Okay, so T1 to Tn are indices, which each ranges from 1 to T. Mm-hmm. Yeah, psi is the ground state. Yeah. No, you give the quantum state. QMA is that you have quantum witnesses, right? Yeah. That would be QCMA that you're thinking, but yeah, there are also connections there, but okay. So you have WE, okay, and then WE sub tau I matches the ith Pauli observable of HL. Okay, so the way these taus are chosen is that, so WE is going to be some sequence of right. So WA, for example, right, it's some sequence of identity XZ whatever, and so tau, all right, and HL, right. So we wrote it as this, right, a gamma I HI, and HI is going to be a tensor of Pauli's as well, right. So HL is, for example, going to be like lots of identities, and then some XZ identities and so on, right. So now this tau is going to take, what is the notation? Yeah. So this tau is basically picking some index. So for example, to match this, the first one, it's going to pick from WA, it will say pick the second index, first index, 3. So this would be, so tau 1, because there's t many non-trivial entries, so tau 1 is going to be, say for example, 2, which is the second entry here, and then tau 2 would be, for example, whichever one matches 3, and so on. Okay, so that's what the notation is saying. And now the claim is that you set assume this happens with high probability. Okay, let's not worry about this. So suppose there's a high enough probability this happens, and then the verifier sends T1 to Tn to prove a 1. Okay, so to prove a 1, we are going to send. We will write it down properly in a moment. So you send these indices to prove a 1, and the job of the first prover is to teleport the ground state on those qubits using the EPR halves that he has to the other prover. Okay, so it's going to, it'll transport, say for example, second and third of the ground state psi, so second and third qubit using the EPR pairs they already have to the other prover. Okay. Okay. And of course, tau 1, tau n were chosen such that the first prover teleports the ground state of H in the exact positions of the measurement according to HL. So this is what we already did, right? Already explained this. And using these outcomes from the second prover and teleportation corrections from the first prover, the verifier can estimate lambda 0 of H. Right, because it's been teleported, and then the second prover is going to make the measurements, right, the corresponding WA measurements, and those are exactly what you want to estimate the value for the Lth element, right, HL. So you can do that, and then you're choosing L appropriately by the correct weight. So it will be okay. All right. Okay, so so that was the intuition for how the proof works. So this is the same proof but more formally written now. So the Hamiltonian test GH for an XZ Hamiltonian is given as follows. So the verifier performs each of the following with probability 1 minus p and p respectively. So it does the Pauli-Brading test with probability 1 minus p. So this we already discussed, right, where you do all the 3 tests: consistency, linearity, and the magic square, like t copies of magic square in parallel. So that's the Pauli-Brading test. You do this with probability 1 minus p, and then with probability p you do the energy test. Okay, and the energy test is as follows. So the verifier samples W, E and L as written, and then chooses tau 1 to tau n such that HL corresponds to sigma W E tau I, right, which is what we just explained, right. This is what I was writing, right, that so if you take W, you look at this operator, like it tells you X, right, so you apply sigma of W A of tau L, right, tensor L. So this will give you HL, right? It's just by construction. Okay, and then you send the following. So you send tau 1 to tau Tn, or sorry, T1 to Tn, like I was saying, to the first prover, and We to the second prover. Okay. And the first prover gives you some answers, A, B, right, which are basically the Pauli corrections for the teleportation. And the second prover gives you an answer for the measurements. So this is T, okay, this is, sorry, my handwriting is a, so it gives you the answer to all the measurements he's made for all the W's, okay. And so this part looks a little bit mysterious, it will become clear a little later, but what is happening is that you're basically checking if the
But who's teleporting here?
the first prover is teleporting it to the second prover and sending the corrections. Yeah, so they send the corrections to the verifier. So A and B are the corrections.
Yeah, okay, so he's just sending the corrections to the prover B.
Yeah. So he's just done the non-local measurement across the half of VPRs that he has and the witness on the location specified by tau, and then the measurement results are A and B, which will correspond to the corrections. Okay. And so this part is a little bit mysterious. It will become clear when we do the analysis, but let me at least describe what is happening. So you let D be, you define D basically in the following way. Okay, so what is D doing? So D is the same as you get C, right, which is a sequence of T-bit strings. You look at the ith index as indexed by tau, right. So this will basically give you the measurement result for the ith element of HL, right. So HL it's a sequence of these, right. So you're asking for the ith or the lth, whichever. So you pick that. Is that making sense? Okay. So you have, so HL was, for example, sigma WA1 tensor sigma WA2 and so on. Sorry, tau 1, tau 2 and so on, right. So tau 1 is basically encoding which of the qubits it was supposed to be acting on. So tau 1 is basically just the register. And so what you do is, when you measure it, you'll get some answer C, right. So you'll get C as a long string, but C of tau 1 will be the answer for this guy, right. C of tau 2 would be the answer for this guy, and so on. Okay, so you pick C of tau, and then you apply the correction, quote unquote. Okay, so D is the corrected result, if you like. Okay, and similarly this one is the corrected result, and the correction will obviously depend on whether you are measuring X or Z, right. So you'll have appropriate corrections, and then there's this predicate. So this part is not very clear. It will become clear why they define it like this. But you check the result of the measurement, and you check if it matches the sign of gamma sub L, where gamma sub L was the coefficient, right, in this expansion, gamma sub I, that's the coefficient. Okay, so you check whether the product of all the D's after the correction for teleportation, quote unquote, matches the sign of gamma. Okay, because that's how you will add or not add to the expectation of the estimate for the Hamiltonian. Okay, so it will become clear more when we do the analysis, but this is roughly the intuition. And so if it doesn't match, then you accept, and if it does match, then you reject, but with probability gamma sub L. Okay, so it's this part is the magic part, and you'll see how it falls in place. Okay, so now before we give the actual proof of the theorem, we are going to state two lemmas. Then we'll use these lemmas and prove the theorem, and then we'll come back and prove the lemmas. Okay, so that's the idea. So let's look at the lemmas. So the first lemma says that suppose H is some XZ Hamiltonian, right, and G is the game as we just described above, and they just define this quantity W sub H, capital H. So sub H is supposed to denote honest. Okay, so it's partly honest. Then this quantity is 1 minus P. It has some expression like this. Okay. So what this says is that if the provers use the honest strategy in the Pauli braiding test, okay. So suppose that this were the case. So you're looking at a restricted strategy where you're assuming that they were following the honest strategy for the Pauli braiding test. Okay. then the maximum probability of acceptance in GH, in the game that we just described, the energy test game, is going to be given by WH capital H. Okay.
What is P0?
P is this parameter that we had, where is it? That you do the first test with probability P and the second with 1 minus P. Okay. All right. Okay. And it can be achieved if the first prover behaves honestly in the energy test. Okay. So, the first statement was that it was bounding the maximum probability. It's giving you an upper bound that if you follow PBT, if you follow honestly the if you use the honest strategy when you're playing the PBT part of the test, then the maximum probability with which you can win is this quantity, and this can actually be achieved. Okay. Assuming that the first prover behaves honestly in the energy test, which is that he teleports correctly the witness. Okay. So that's the first lemma. So we'll look at the proof in a little bit, but is the statement clear? Yeah? Okay. And then lemma 8 says the following. So it says let H, GH and WH be as we defined it just a second ago in the lemma above. Then for each eta strictly greater than 0, there exists some P of order square root n such that omega star GH is at most this quantity, omega sub H plus eta. So what it is now saying is that remove all restrictions from the prover. So assume that it's an arbitrary prover doing whatever they want. Even then, the maximum probability with which they can win is upper bounded by the semi-honest strategy, right, that we sort of looked at where the PBT was honest, plus some correction eta, some small factor. Okay, so these are the two lemmas. We'll prove them in a moment. But let's see how we can use them to prove the theorem. So the theorem is the following. So suppose, so lemma 5 states that from H, one can construct H prime such that the gap between the lowest eigenvalues of H prime becomes constant, right, from alpha and beta. So this we saw already, right. And also crucially, H prime continues to be an XZ local Hamiltonian, right, because it only added identities, right, you remember the strange form. Okay. So in what follows, we are going to bound the maximum acceptance probability of the Hamiltonian test on H prime, relating it to the ground energy of H. Okay. So we are going to run the test on H prime, right. So G was the compiler, right, that takes a Hamiltonian and gives that energy test. So we are going to run that on H prime, and then we will relate it to the ground state energy of H that we started. Okay. So from from lemma 7, lambda sub 0 H is at most alpha. This implies that omega star for H prime, right, is going to be this quantity. So let me actually make two windows now. You can see still, right, or is it too small? It will just be for a second. Let me open another window. It will be easier to refer to things, otherwise I'll be like, oh, look at this. So now we're looking at lemon. Oh my god, I don't know what's happening to me. So we're looking at, yeah, let's just call it lemon from now, so I don't have to embarrass myself. So lemon 7 says what? Right, so lemma 7 says, oh, where did lemma 7 disappear? Huh? Uh-oh. Oh, I think I changed the order of things. That's why. Sorry. The paper has it in a slightly different order. Okay. So lemma 7 recall is just saying that you have to combine these two, I guess. All right. So lemma 7 says that there exists at least one strategy, right, with which you can win with probability omega sub h, right? This much is clear because it says that if you're honest, semi-honest, then you can win with at most this, and the later part of the lemma says that you can achieve this if you are if the first prover is honest. So certainly you can win with at least omega h probability, but we were applying lemma 7 on the game G, but with h prime, right? And for h prime, what do we know? We know that this lambda 0 is at most half, right? So you make that substitution, you get a quarter, and everything else is the same. We've not done anything else, okay? And we use the fact that when the Hamiltonian, the original Hamiltonian, has at most alpha ground state energy, then omega star will have omega star of h prime would have at most half, which we substituted to get this, right? So we've not done much, okay? And then the second note is that from lemma 8, which is right here, we get that for any eta and for some p smaller than some constant times root eta, if lambda 0 h is greater than beta, then omega star g h prime is going to be this quantity, except that now we have to use instead of lambda 0 h being half, right, we have to use lambda 0 h being 1, right, because of this lambda 0 h prime being 1, correct? So when you do that substitution, you're going to get you can simplify it, and then this is the expression that you end up with, okay? Now the convention is that you can choose eta prime to be this quantity and take it to be strictly greater than 0, because the constant c you can choose, right? So you can always choose it to be the case. And then from this it follows that when the original Hamiltonian has at most alpha ground state energy, then you win with probability at least c, and when the original Hamiltonian has at least beta energy, ground state energy, then you win with probability at least, at most c minus eta prime, right? We just did a substitution, okay? So we're getting close, right? So we already have a game, assuming these lemmas, we didn't actually do the hard work, we're just using the lemmas, so you have to prove the lemmas, but assuming them, you have this separation. And now here's this last little step, which is that how you go from this gap to a constant gap, because eta still seems to depend on what does eta depend on? Eta depends on eta was a free parameter. So I guess we want to change this c to be whatever, half plus delta, half minus delta. So you basically need to adjust things a little bit in the acceptance and rejection. And the way this is achieved is as follows. So you utilize the following game. So you accept without doing anything, you just accept with probability half minus some constant, okay? You reject with some probability, which is this, okay? So together these constitute a probability half event, and so the remaining probability you use to play the game G that you had originally, okay? And then you can check, you can just do the calculation, and you'll see that when you're winning with at most half alpha probability, when the energy is ground state energy is at most alpha, you'll win with half plus some constant, and if it's at least beta, the ground state energy, then the game will win with probability at most half minus some constant. And so this gives you the constant gap that was asserted in the paper, okay? But it remains to show the actual thing. So before we do this, one quick corollary. So everything we've done so far is for QMA, right, in the sense that you have this witness and so on. We haven't really talked about BQP directly. But for BQP also there is something called a circuit to Hamiltonian construction. So what you can do is you can show that, so very, very informally, you can show that so if you have a circuit C, which is a BQP circuit, then you can transform this into a Hamiltonian, like a local Hamiltonian actually, such that if it's accepting, so if C was yes, then H has ground, low ground energy. So basically lambda 0 H is, the way we have to, lambda 0 H is below some threshold, let's say, what were we using, alpha? and if C is no, then lambda 0 of H is at most, or it has to be at least, sorry, beta. Okay, so starting from C, you can construct this local Hamiltonian, which has this property that if it's a yes instance, the ground state would exist, and otherwise it wouldn't, with alpha minus beta having like some appropriate gap. And one can construct the witness easily. So for CES, psi say H psi equals alpha psi can be constructed, efficiently constructed. Okay. So for a yes instance, so given a circuit, I can construct the corresponding Hamiltonian and describe the witness to the prover, and then I can run this same procedure. Okay, so the corollary is that if you have what we already have, you can use this circuit. So this is called the circuit to Hamiltonian construction. We didn't have time to do this. This was also very beautiful circuit to Hamiltonian construction. Yeah, so basically to get BQP verification as well, just from the statement. All right. So in the last 15 minutes, let's try to do the proofs of. Yeah, it's a BQP circuit.
You reduce what exactly is the result?
Oh, so given a classical description of C, you can give a classical description of H, and I guess you can also give a classical description for how to construct psi, such that this Hamiltonian has that property. If C happens to be a yes instance, so yes instance meaning you run the circuit and it outputs 1 with high probability, then the ground state would be lower than alpha, the ground energy, and if it's a no instance, then the ground energy will be greater than beta. And you can also construct the witness efficiently. So with QMA you don't have this guarantee rate, because so here you can do the whole thing. Yeah, sounds good. Okay. So finally we have the proof of lemma 7. So proof of lemma 7 says what? It says that, okay, so lemma 7 first of all was this statement, right? We wanted to show that you win with probability at most. So if you're honest for the Pauli braiding test, right, then you win with probability at most this omega sub h, right? That's the claim we want to prove. Okay. So the first thing we notice is that when you're running PBT, whether you run PBT or ET, these are indistinguishable to the second prover, because because the second prover was just getting to measure W, right? If I remember well, let's see. So as in PBT, the verifier sends WE to the second prover, right? So which is also what we're doing in the braiding test. Okay, so what that tells us is that if the prover is following the honest strategy for PBT and it cannot distinguish between whether PBT is being run or the energy test is being run, right, then the behavior has to be identical, right? Because if it were not, then also sometimes in the PBT it would behave maliciously, because it cannot tell which test is being run. So if you assume that the strategy is such that the second prover is run, or PBT is being run honestly, then it also has to be the case that the second prover will run honestly in the energy test. Okay, and so therefore the acceptance probability GH is going to depend uniquely on the strategy for the first prover in the energy test, because the second prover is going to behave just as the honest strategy describes. All right. So now what we do is we let A and B be the answers of the first prover in the energy test, and tau be the reduced state held by the second prover on positions tau 1 to tau n. So is that okay? So A, B are the answers to the energy test. So remember, this is the energy test. A, B are the answers by the first prover, right? And now we're going to define tau to be the reduced state corresponding to these indices, which was supposed to be T1 to Tn. This is the conflict of notation that I was saying, sorry. So tau is the reduced state and T1 to Tn are the indices, okay, after teleportation. Okay, good. Right. And now for a fixed H sub L, the verifier rejects with probability this. Okay. So this is a claim. In the interest of time, let's assume this claim is true. Okay. So one can actually just check this predicate, when this predicate matches or doesn't match, and one can check whether this quantity sort of adds up, because you're rejecting with probability gamma L if the predicate is false, and then this you can check accordingly. Okay. And all right, now measuring the qubit in the z basis with outcome f. Okay, so this is like a cute observation, right? So this we need to make sure we follow. So measuring a qubit phi in the z basis with outcomes f, the outcome being f, which is plus minus, is essentially equivalent to getting outcome -1 to the g f when you're measuring x to the g z to the h phi in the same basis. Okay, so z is obviously not going to change anything because you're measuring z, and x is just going to flip the 0 and 1, right? Whether you're getting the outcome 0 or 1. So that you account for by adding a minus sign corresponding to the x. So you put -1 to the g. Okay, so the statistics are the same, and you can argue similarly for the x basis. And why this is nice is because what this is saying is basically applying the correction, right, for the teleportation. Because for the teleportation you have to either do an x correction or a z correction. So given the answers of the first prover, the following behavior of the second prover are equivalent. So whether the second prover measures tau with respect to HL and gets outcome C, or it measures rho, which is this XOR, this tau conjugated with the Pauli's with respect to HL and gets outcome D. And D, remember, was this -1 to the AI and -1 to the BI, right? Okay, so because this tells you whether you're measuring in the x or z, and whether you measure in the x or z, you will get this -1 factor from x or z depending on which one you measure. Okay, so basically these two behaviors are produce the same statistics. And then the third is that, so using the second point, one can take the product of di as the outcome of HL of HL on rho averaged over all L. Okay, so HL was, I didn't explain it. I thought I had another page. So equation 1, yeah, here. Okay, so equation 1 here, or maybe I can actually get equation 1 from here, it's probably better. Right, so you see equation 1 here, right? So what this is saying is that, so equation 1 was measuring D, right? And we just saw that measuring D is essentially the same as measuring HL on rho, right? Right, because of the Pauli correction. So D is adding these -1s, right? So D, remember, is adding these -1 factors. Okay, I should be able to write, otherwise it gets a bit confusing. Let me open another one. All right. So D, remember, is adding the phase, right? It's adding -1 to the A or -1 to the B on whatever C outcomes you were getting, right? So this is the same D that we're using here. Okay, so it's the product where you added the phases. Okay, Ariman, what's going on? Are you lost completely, or okay? So let's track what we are doing. So we are basically trying to prove this statement, right? We're trying to show that the bound that we had written for lemma 7 is true. So that bound was, there was some, where's lemma 7? So we're trying to show this bound, that if you're honest in the PBT, in the Pauli Brading test, then you win with at most this probability. Oh my God, this is what we're trying to prove. Okay, and the way we were arguing was that we first argued that PBT and ET, so the Pauli Brading test and the energy test, are indistinguishable for the second prover. So far you were with me, I think. And then we were trying to argue that, okay, and then it's clear that the value of the game would depend on the strategy of the first prover in the energy test, right? Everything else is honest, correct? Just by assumption. Because by assumption you were honest in the PBT, and then, yeah. The communication bits are?
The teleportation, they are conveyed honestly.
Right. Here we are trying to, not quite. We are basically just going to show that the expression that we have written, you can relate it to the measurement of the Hamiltonian, and the state tau could be something else. It's not guaranteed to be the right thing, because the first prover is the one that is sending the teleported bits, right? So that they can deviate. We're not saying that they're not deviating. So they can send some other bits. So okay, so you can look at the details later then, I think, if it's getting confusing. So the important thing here is that the prover is going to send B, right? What is it? BB prime, I forget the notation. So it's sending A and B, right? Which are the corrections for the teleportation. And using this observation that I mentioned here, you can show that this quantity that we wrote here, we wrote it for a reason. Okay, so the D already has this exponentiation factors. Okay, and because D has those exponentiation factors, and from the second note, right? So the second note is saying what, that it's equivalent to measuring. So instead of measuring tau on HL and getting some outcome C, you basically measure tau with the corrections and report outcome D, right? These two things are equivalent. So what that means is that you essentially already removed the teleportation from when you're looking at expectation of product of D. So the teleportation part has already been corrected. Okay, so it follows that in the energy test, the verifier rejects with probability 1 by m, and this sum, and this last term becomes just trace rho of HL, right? Because rho is just this corrected thing, and that's what's being measured. Okay, you can look at it at piece if it's getting confusing. It's nothing very deep. And then now what we've done is we've been able to relate it to the Hamiltonian, right? Because this was on average over L, right? So when you average over L, you would get trace rho H. This gamma L, right? And clearly this value is minimized when rho is the ground state, right? Because this was the probability with which it rejects, and to reduce the rejection probability, you want to reduce this additional term, and this is the smallest, because the first term doesn't depend on anything, right? It's just a function of the Hamiltonian. The second term depends on the state, and this you can minimize by sending the ground state. Okay, so the overall acceptance probability, so this was the rejection probability that you were minimizing, so the acceptance probability is just 1 minus p times p being, because that's the probability with which the energy test is done. So 1 minus p times this, and this is exactly what we define to be omega h. Okay, and it turns out that you can also achieve this by basically teleporting the correct ground state. Okay, So that's the statement, and yeah, so that basically completes the dilemma, right? Because the best strategy that you had was to send the ground state, and we already showed an upper bound on the acceptance probability by showing that you have to at least reject it with this probability. Okay. And then the last step in the last 3 minutes is establishing that this lemma 8, right? And lemma 8 was basically saying that, so here we said that we already assumed that you were honest in the Pauli braiding test, right? But you may not be, right? And then how do you handle that? And so this is basically handling that part. So what you do is, so we know from theorem 2 that okay, no, wait, I should write this down. So suppose that the strategy being followed by the provers is such that with probability 1 minus epsilon, they get accepted in the Pauli braiding test, and with this 1 minus some other probability, they get accepted in the energy test, okay, for some epsilon and delta. So you can write this. So it's just a general strategy, and you're putting some bounds. And then the key observation is relatively straightforward. So the key observation here is that because we have the self-testing theorem for the PBT part, right, that if you're winning with high probability, you have to be close to the honest strategy. So you leverage that. So the way you do it is you say that if you're winning with probability close, high enough probability because it was 1 minus epsilon, then you're going to have some isometries VA, VB, right, which are root epsilon close. And then you define SH to be the strategy where the provers follow the honest strategy, okay, in PBT. And for ET, the first prover performs the same operation as S, but using the isometry, but otherwise it's the same, okay. So basically we are defining SH to be the strategy where the first prover is honest for PBT, and for ET it uses the up to isometry is the correct strategy, okay. And now it says because the measurements performed by the provers in S and SH are close, right, root epsilon close, considering the isometries, the distribution of the corresponding transcripts have statistical distance at most root epsilon, okay. So if you're honest if you're winning the PBT with a certain probability, right, then your strategy has to be close to the honest strategy, right. And so it's saying that instead of considering the actual prover, you consider S sub H, which is honest. The first prover is honest in the way that it's is described. Then the transcripts in the two cases, where you use the malicious strategy versus where you're using the honest strategy, semi-honest strategy, the transcripts will have essentially the same distribution. That's what it's saying, okay. Okay, so the provers following S sub H are going to accept ET with probability this, and this is basically just following from the fact that the strategy is exactly the same as the previous case. So SH, the ET part is the same, right? It was only the honest part that we changed. That's what semi-honest means, right? So the second part is essentially the same as what we had before, except for this little extra factor, right? Because of the fact that the strategies deviate by just this amount, so the probabilities will change at most by that amount compared to S, right? And since SH follows the honest strategy in PBT, it follows from lemma 7 that so lemma 7 was this one, right? So lemma 7 was exactly the statement when for semi-honest provers, right? Semi-honest in the sense that the provers were honest when they were doing the Pauli braiding test. So we already had an upper bound on the winning probability, right? So one can combine this quantity with the upper bound on the winning probability, right? And this would give you an upper bound on the probability that SH wins. Sorry, that S wins in the energy test, right? So the structure was you start with S, you argue that S and SH are going to be negligibly close, you prove the result already for SH, okay? So you leverage all those things to get this inequality on the success probability of S, Okay. And now the overall success probability, so that was the success probability for the energy test. The overall success probability would be 1 minus p times the success probability in the Pauli braiding test plus p times the success probability in the energy test that we just proved, right, which is this quantity above here. So you can put it together and it would give you, you'll get your omega h and then these extra little factors, and then one can, yeah, so then you have to massage it a little and then you should be able to get it to the form that we need. You have to play with the parameters a bit, then you get that you win with at most omega h plus eta. Okay, so I think, yeah, we are sort of out of time, but that's sort of the idea. So first you try to prove, assuming that it's playing honestly in the Pauli braiding test, and then you get some bounds, and then you relax that by using the self-testing property of the Pauli braiding test to argue that that also doesn't change. And then you're able to combine it to say that even in the most general case, you will not be able to win with probability more than some quantity, which is related to the Hamiltonian, which is what we wanted. So that was verification. Sorry, it had to be a little bit fast because we ran out of time for the last lecture. But, okay.
If we read the paper,
Yeah. Sorry, what?
if we read it,
Yeah, it'll be much clearer. Yeah, for sure. Okay. All right then. Thanks, you guys.